Hello students, welcome back to my channel. You are watching All Over Physics. In the previous video, we started solving the exercise questions from chapter 1, that is Introduction to Physics of class 11. That was part 1 of our 3-part series. If you have not watched that video yet, make sure to check it out first for a better understanding of the concepts. In today's video, we are continuing with part 2, where we'll solve more questions from the same exercise with clear step-by-step explanations to help you build a strong understanding of the concepts. But before proceeding further, if you find this helpful, please like, share and subscribe to the channel for regular updates and more such videos. We'll start with problem number 6. The problem states, find the dimensions of the specific heat capacity C, the coefficient of linear expansion alpha, and the gas constant R. And the corresponding equations are given below. We'll take the first equation, that is Q is equal to mc T2 minus T1. So in the equation, Q is the amount of heat energy, M is the mass, T2 minus T1 is the temperature difference. So we have to find the dimension of specific heat capacity, that is C. Therefore, we will take C on the left hand side. So rearranging, we can write it as Q divided by M T2 minus T1. Or other way, we can write it as Q divided by M into delta T. Now we have to find the dimensions one by one. First comes the Q, which is nothing but heat energy. And already we have derived in our previous video that dimension of heat energy is ml square T to the power minus 2. Then come mass, which is represented by capital M. Then comes temperature, that is delta T, which is nothing but K. So putting these values in the main equation, we can derive the dimension of specific heat capacity as ml square T to the power minus 2 divided by capital M into K. This M and M will cancel out, therefore you can write M to the power 0 L square T to the power minus 2 K to the power minus 1. Now we have to find the dimension of coefficient of linear expansion alpha. We'll write the corresponding equation, that is LT is equal to L naught 1 plus alpha T2 minus T1. If L0 is the original length at temperature T1, then when the temperature is changed to T2, the length will also be changed to LT according to the formula, where alpha is the coefficient of linear expansion. Now we'll rearrange the equation. LT minus L0 will be L0 alpha T2 minus T1. Then we'll take alpha on the left hand side and the corresponding equation will be LT minus L0 divided by L0 T2 minus T1. Or other way you can write delta L divided by L0 delta T. Now we know dimension of delta L is represented by the symbol capital L. L0 is also length, therefore it is capital L. Then comes the delta T terms, which is nothing but temperature, and temperature is represented by the symbol K. Therefore, we can write the coefficient of linear expansion as L divided by Lk. Therefore, the dimensional formula will be K to the power minus 1. Next, we have to find the dimension of gas constant R. So we'll write the corresponding equation, that is PV is equal to nRT. This is ideal gas law. where P is the pressure, V is the volume, R is the ideal gas constant, T is the temperature, and N is amount of substance. Now taking R on the left hand side, we can rewrite the equation as PV divided by NT. Now pressure is force divided by area, and we have already derived dimension of pressure is m L to the power minus 1 T to the power minus 2. Then comes volume. Volume is length cube. Then comes amount of substance whose dimension is mole. And then comes the temperature, which is represented by capital K. Therefore, putting all these values, we can write dimension of gas constant R as m L to the power minus 1 T to the power minus 2 into L cube divided by mole into K. So rearranging, we can write the equation as ml square T to the power minus 2 K to the power minus 1 mole to the power minus 1. Now we'll take the next problem. The problem is stating taking force, length, and time to be the fundamental quantities, find the dimensions of density, pressure, momentum, and energy. So one by one, we'll find the dimensions. First comes the density. Now density is mass divided by volume. And from Newton's law, we know force is equal to mass into acceleration. Therefore, we can write mass as force divided by acceleration divided by volume. Now we have to write the dimension. First comes the force. We know the dimension of force is ml T to the power minus 2. Then comes volume. Dimension of volume is L cube. Then comes acceleration. Acceleration is L T to the power minus 2. But closely look at the problem. It is telling we have to take force, length, and time as the fundamental quantities. Therefore, instead of writing force as ml T to the power minus 2, we'll directly take F. So we'll put the values in the main equation, and therefore we can write dimension of density as F divided by L T to the power minus 2 divided by L cube. Therefore, rearranging, we can write the equation as F L to the power minus 4 T square. Next is pressure. The pressure is force divided by area. We will take force, dimension of force as capital F, and dimension of area is L square. Therefore, putting these values in the main equation, we can write the dimension of pressure as F divided by L square. Therefore, it is F L to the power minus 2. Next, we'll take momentum. Now, momentum is mass into velocity. And just now we told mass is force divided by acceleration. Therefore, we can write dimension of momentum as F divided by LT to the power minus 2 into LT to the power minus 1. Therefore, we can write dimensional formula for momentum as F into T. Next, we'll take energy. Now, formula for energy is half into mv square. Therefore, we'll take dimension of energy as dimension of mass into dimension of velocity, and there is a square term. The half we are not considering because it is a constant and constant had no dimension. Now mass is force divided by acceleration into velocity square. Therefore, one by one we'll write force is represented by F, then acceleration is Lt to the power minus 2, then velocity is Lt to the power minus 1, and there is a square term. So rearranging, we can write the dimension of energy as F into L. We'll take the next problem. The problem is stating, suppose the acceleration due to gravity at a place is 10 meter per second square, then find its value in centimeter per minute square. The problem has given value of g, that is acceleration due to gravity, as 10 meter per second square. Now meter per second square is in SI system, and the problem is telling to express it in centimeter per minute square. Now the problem can be directly solved by converting meter to centimeter and second to minute. But since it is a problem of the chapter units and dimension, we'll solve with the knowledge that we have learned in the chapter. Now we know the dimensional formula of gravity. We'll write within square bracket g is equal to L t to the power minus 2. Then I'll write g in meter per second square divided by g in centimeter per minute square is equal to, so this is for length column and then this is for time column, and there is a minus 2 exponent. Here we will write 1 meter, here we will write 1 second, then down we'll write 1 centimeter, and here 1 minute. Now we know 1 meter is equal to 100 centimeter divided by 1 centimeter into 1 second. Now 1 minute is 60 seconds. We'll write 60 seconds to the power minus 2. Therefore, it will be 100 into 1 by 60 to the power minus 2. That is 100 into 3600. Therefore, you can write 36 into 10 power 4. So, the relation between 1g in meter per second square is 36 into 10 power 4, 1g in centimeter per minute square. Now the problem is telling gravitational value is 10 meter per second square. So the converted value will be 36 into 10 power 4 into 10 centimeter per minute square. That is 36 into 10 power 5 centimeter divided by minute square. We'll take problem number 9. The average speed of a snail is 0.02 miles per hour and that of a leopard is 70 miles per hour. Convert these speeds in SI units. So we'll solve the problem in the similar way as we did in the case of problem number 8. The problem has mentioned average speed of a snail as 0.02 miles per hour and speed of a leopard as 70 miles per hour. Now we have to convert the values in SI unit. We know dimensional formula for speed, which is represented by the symbol V as L t to the power minus 1. Therefore, we'll write 1 miles per hour divided by 1 meter per second is equal to, this is for length column and this is for time column. So top it will be 1 miles then 1 hour, and down it will be 1 meter and 1 second. Now we can write 1 miles as 1600 meter divided by 1 meter into 1 hour is 3600 second divided by 1 second to the power minus 1. Therefore, we can write 1600 into 1 by 3600, that is 16 by 36, that is 4 by 9. Therefore, the relation is 1 miles per hour is equal to 4 by 9 into 1 meter per second. Therefore, speed of a snail in SI system will be snail's speed is equal to 4 by 9 into 0.2 meter per second, which will be approximately 0.0089 meter per second. And leopard's speed in SI system is 4 by 9 into 70 meter per second, which is approximately equal to 31.1 meter per second. We'll take problem number 10. The height of a mercury column in a barometer in a Calcutta laboratory was recorded to be 75 centimeter. Calculate this pressure in SI and CGS units using the following data. First, specific gravity of mercury is 13.6, density of water is 10 cube kg per meter cube, and acceleration due to gravity is 9.8 meter per second square at Calcutta. Now the formula for pressure is given as H rho G. Now formula for pressure is given as H rho G, where H is the height, rho is the density, and G is acceleration due to further we can write height. Now density is mass divided by volume, and acceleration due to gravity is length divided by time square. Now one by one we'll write the units in both the system. We'll make a table, SI unit and then as the CGS unit. First comes length, then is mass, then is volume, finally we have time. Length has unit of 1 meter in SI unit and 1 centimeter in CGS unit. SI unit of mass is 1 kg and CGS unit of mass is 1 gram. Then volume is meter cube, whereas in CGS system it is centimeter cube. SI unit for time is second and CGS unit for time is also second. Now again we'll write the formula for pressure, which is H rho G. First we have to express it in SI system. The problem has given height as 75 centimeter, which is in CGS system. Therefore in SI system it will be 75 divided by 100 meter. Then comes rho, that is density of mercury. The problem has given density of water and it has told the specific gravity of mercury. Therefore, density of mercury will be 13.6 times 10 power cube kg per meter square. This is in SI unit. If we convert it in CGS unit, it will be 13.6 into 10 power 3 into 10 power 3 divided by 100 cube gram per centimeter cube. This is in CGS system. And finally comes acceleration due to gravity. It is given as 9.8 meter per second square. So again, it is in SI unit. If we convert it in CGS unit, it will be 9.8 into 100 centimeter per second square. This is in CGS system. Therefore, pressure in SI system is 75 divided by 100 meter into 13.6 into 10 power cube kg per meter cube into 9.8 meter per second square, which is equal to 99960. And in SI system, unit of pressure is Newton per meter square, which can be approximated as 10 into 10 power 4 Newton per meter square. Similar way, pressure in CGS system is 75 centimeter into 13.6 into 10 cube into 10 cube divided by 100 cube gram per centimeter cube into 9.8 into 100 divided by 1, which is approximately equal to 10 into 10 power 5. And in CG system, unit of pressure is dyne per centimeter square. Alright students, that's it for today's lesson. I hope you found it helpful and learned something new. We'll start our video with part 3 of the exercises of chapter 1. If you enjoyed the video, make sure to hit the like button, and if you're new here, don't forget to subscribe the channel for more contents every week. Thanks for watching All Over Physics. See you in the next video.